Okay, good morning. All right. Okay, let's check. Yeah, last time we have finished here. Okay, so I think you have learned the some of the basic concepts on stress strain behavior on the material science, right? So I hope if you are really want to pursue your maybe study or career or anything that related to material science, the stress strain behavior, this one here, this will be really essential. Okay? So even for some, I'm not sure, back in my country, if you are material engineering or material science engineering, you need to be able to draw the steel carbon diagram like this one with stress strain curve with exact stress number. What's the yield stress for the carbon steel, and what's the ultimate strength, and how about the elastic behavior, plastic behavior, ductility, and so on. And you should be able to do that like in board. And even aside from this stress strain curve, as a material science, for the basic part, if you know one or two phase diagrams, and usually a typical phase diagram for material science is the carbon steel, right? The carbon steel. Whereas the austenitic steel, the ferrite, blah blah blah, the alpha ferrite, and you need to be able to know exactly like the temperature, at least the one that is the large portions. Okay, so that's the thing. As a material scientist, that's the one that you need to pay attention to, because that's really basic. So the stress strain. So we develop, or we showing you the behavior. Okay, so elastic behavior, and then plastic behavior, and then elastic region, yielding, strain hardening, and I think I mentioned strain hardening in the latest Moodle post. I put some links. If you have time, you can check that out. I think that's one of the simplest video explaining the dislocation movement and why the dislocation movement makes in a macro scale makes a hardening. It makes this called the strain hardening. So when you strain, it's become harder, and this is because of this strain hardening. Then we know how to treat some materials like metals. If we strain them, like we take some rolling, like hot rolling, cold rolling, we can improve their property. We can improve their characteristics. Okay, now let's go for the next. Okay, so we have strength, stiffness, ductility. We have discussed about this last time. And another thing, although this is not in a standard unit, this is KSI. KSI is the kilo per square inch, kilopounds per square inch. That's KSI. This is the strain in inch per inch, but if in standards it's millimeter in millimeter per millimeter. So if you go for the standards, it should be millimeter per millimeter. The KSI here usually MPa. Okay. So although this is KSI, the idea is still the same. Okay. We have two curves now. What does that mean? Okay, so this is two scale. We have two scale. The first one is like the original one like before. We have the elastic yielding, and then this is plastic and up until fracture. Okay. The second one here is to focus more on this scale here. This is the elastic. So this is elastic and yielding. Okay. And if you see the number, you have two numbers. The top one is for the original one. The second one is for the elastic. Okay. Sometimes they provide these two curves because sometimes we need to make sure or we need to confirm what's happened in elastic. What's the number and what's the proportion. Okay. So sometimes they give you these two curves. Okay. So if you like maybe have like a problem solving and you see the curve has a two curve and you have no idea what it is. It's actually, the first one is the original curve. The second one is the, like you zoom in to this area and it becomes this, okay? With this number, okay? So we have two scale, okay? Two scale. So let me write here, we have two scale. What? Scales, okay. So this is the elastic, and then this is the yielding. Okay, and then for some other material, well, it's still in steel family, like a carbon steel and other steel alloy. Depends on how we mix them with the other metals, or maybe put some more carbon or more impurities, different impurities, we can have different property as well. Okay. And then if you look here, we have a typical specimen and how they break here. Let me zoom in so you can see clearly there. Okay. This is what we call, sometimes we call this a cup cone fracture, cup cone fracture. And it is a typical fracture in a ductile material, okay? In ductile material. So this is a cup cone fracture. And this is, I think this is hot rolled specimen. This is hot rolled specimen, which means this is ductile material. And ductile material will typically have the cup cone fracture. Okay. You don't bring, but later, how we could see the fracture, it's actually we learned later. It's based on the Mohr circle, M-O-H-R, Mohr. I'm not sure how to say that, but I think it's Mohr, not more as more, but Mohr, like it's H, using the Mohr circle to determine brittle or ductile materials. If you know chalk for writing in a board, let me write for you. Chalk. Okay. You can try if you have in your home. Later, maybe next week, I'll try to bring one in class to show you how the brittle materials will fracture. Okay. If you twist the chalk and you pull the chalk, you will see the difference. Later we will see. This is a brittle material. So that's one way to show the difference between the ductile material and the brittle material. Okay, and we could see the relations, how the typical fracture using Mohr circle. We will have Mohr circle, I think, still a few chapters later. Okay. But that's just the introduction. Okay, another one is this typical aluminum alloys. And you see, no yielding, like not really clear which one is the yield, right? So like I said, we need to take the offset rule. Okay, offset rule. Take 0.2%, and then take the proportion, the same slope, and that's what will be your yield stress. Okay. And this is the specimen, control specimen, the cup cone fracture. Okay, as I said, the offset, this is how we are using our offset. Okay, although it's not in the standard unit, it's in KSI and inch, but the method is still the same. We're just using the 0.2% offset, and take the slope proportional to the slope, and that will be our yield stress. Okay, our yield stress. And then this is how brittle ductile relations, if we put into stress strain diagrams. And this is one example, fracture surface on a tensile test. Okay, on a tensile test. And then this is, imagine this is the some alloy that is super plastic. From original size, we deform like a rubber, right? It's, maybe similar to rubber. Okay. So there's some ways. So this is about ductility. So for ductility, we can take the methods. First is the elongations, and the percent elongation. So this, let me write here, percent elongation equal to the final length, the original length, divided by original length, and then multiply by 100%. So L0 is original length or original gauge length, and LF is the length of gauge section at fracture. Okay, so that's how we compute ductility, the first method. The second method is the percent reduction. Or percent reduction in area, to be precise. So we are computing the cross sections. Okay, so how to think this ductility comes from? How to think why you need to take this elongation or the area? If you see the original size, the length become larger, become more longer, and then you see the cross section, the area become smaller, right? Length longer, and the cross sections become smaller. Okay, so we could write the percent reduction in area is equal and this is the cross section or original cross section, and this is final cross section at fracture location. Okay, there's another sections, but I think I will skip that, about plastics, composites, about creep behavior, but I think I will skip that. But let's see. Perhaps one more section about this material property is about elasticity and plasticity. Okay, imagine that we have these two picture. Okay. Let me go here. So this is the elasticity and plasticity. Okay. Now let's say we start from the left picture. Okay, the picture on the left, that we have point A, B, C on the curve, right? Point A, B, C. And in the curve, it was mentioned that from A to some point C on the curve, it's still on the elastic behavior. So perhaps this is a type of aluminum, perhaps, because not showing any building like steel. So maybe aluminum. So elastic behavior is if we take push or give force. Okay? If we give loading, if we put some loads, it goes up, maybe put until before C, and then we release. Okay? Or maybe up until B, okay? And then unload. So unloading from B. So the sigma stress or the stress on B is less than the stress on this elastic or yield stress, okay? Or yield stress. So less than that, and then it will retrace back to the original loading path. Okay? So it goes back to here, and in visuals, what's happened is it goes back to original shape. Like you play with your ruler, and then, oh, it's back. Okay. If not, then maybe your ruler will be broken. Okay, so that's elastic behavior. Okay, look on the right, and look on the right. What's the difference? So if we get put loads until D, so we passing C point. If we release, we trace this line, which is proportional to the elastic here. So the way you try to imagine this, okay, if this is the curve, so first draw the slope from the original point, and then when you trace back, like release the loads, you are going to make line that is proportional, okay? Same slope. And what's this? This is the length that deformed. How much the shape has going to be deformed. Okay? So we say that this will be the permanent deformation. Okay? This will be permanent deformation. How this much? Okay? This permanent deformation. And this is going to be the recovery. Okay? So of course, like maybe like the Play-Doh, like for baby they play clay, like a clay, right? And perhaps some part of it, but maybe clay is too squeezy. What else? Yeah, maybe something other type of materials. When it goes back, maybe some part of it is permanent. This goes the plastic deform or plastic deform, if you want to take that as some plastic deformation or plastic deform. Okay, and then some part of it will recover to original positions. Okay, that's one idea. Okay, how we relate the elasticity, plasticity, and if there are some parts of plastic deformation, how much is the recovery? Okay, we can use this diagram, this method, this slope, to see how much does the shape will recover. Or we could say the C is elastic limit. We can also say this, but actually they're the same thing. The yield stress, blah blah blah. They become plastic, they form the same idea. I don't know why they mention different keywords, but it's actually the same thing. Okay, I think we can skip the other part and let's focus on the next one. Is more about the linear elasticity. So I think linear elasticity, as in your basic physics, we can start with the Hooke's law. Okay. And also we are going to use the Poisson ratio. It's not Poisson, but Poisson. Okay. It's in the name's person. It's a person's name. So the Hooke's law, let me write in terms of, so we write the elastic modulus and the strain. Okay. And actually it's the same as what we did in the stress strain before. It's based on the Hooke's law actually. This x is just in the same axis, okay? The axis of the stress and strain. So E is the Young's modulus. Or modulus elasticity. GPA or MPA. And the sigma, for the Hooke's law to be applied, we need to restrain the sigma or the stress. This is before the plastic, okay, before the plastic. This is yield. So the Hooke's law valid for any uniaxial. Okay. Uniaxial tension or compression within the elastic. Within the elastic region or linear portion. Okay, I think that's just a review. I think this is quite simple. But the one that you need to take care much is the Poisson ratio. Why make ration like with n? The Poisson ratio, usually we write with these symbols, is equal negative strain at the transversal over strain at longitudinal. Or we write strain transversal, let me just write it like that, and minus strain at longitudinal. Or let me just write as long and trans. Okay, there are one example, but I think I will just focus, continue a little bit. And I think for the example and all the other sections will be continue on Monday. So let me continue first. So that's Poisson ratio. So Poisson ratio is the ratio. So imagine that when we have this material like that, this is when we take a tensile, right? Let's imagine that this is the original size and then it's become this. Okay? So there are changes, right? There are changes in this directions and these directions. Okay? So why we need this negative? Okay? How does it come? Where does it come from? Because we want to make sure that the ratio is positive. If we remove this negative, the ratio, this strain, will be negative because the strain is going to be the transversal and the longitudinal will be a negative value. So we need to multiply with negative. So we have a positive. We will check the example. But that's how the the transversal and the longitudinal. Okay, now continue a little bit on the shear stress. Okay, shear stress. Shear stress, shear strain, and shear modulus. Okay, now the shear stress, if we got the picture here. So let's say we have a distribution of shear force on a section plane. We can say that if we distribute on all, and usually we just simplify our problem like it's uniform, nothing really happened in between. So we could take all that distributions and make it into one resultant force, right? Resultant shear force. And actually, the definition of the shear, we write shear like in tau, is using limit as the delta A getting 0. Okay. The V here, the V, this one is the force, the shear force. Okay. So basically, it's the same or similar with the original normal stress, but the difference is the direction. The normal is normal to this plane. Okay. But here is they are the same axis with the plane. Okay. We call it the shear force. Okay. Or sometimes we call this a, tangent force. but it's not really common, but we usually say just shear force. And we could rewrite this in terms of the integral. The shear force equal tau dA. And the average of the shear stress and then there are what we call the direct shearing or direct shear. This is like the scissors. What else? The anything that cuts something, it's direct shear. So the force directly acts, but parallel to the particular surface. So for example, the scissors. This is the paper. Okay, and another concept that is important is there are at least two type in our course of shearing. Okay? The first one is the double shear. This is the direct shear. Let me write here, single shear and double shear. Oh, let me write on the left. This is example for direct shear, maybe here. So single shear, double shear. So right here. So single shear, single plane on which the shear stress acts to transfer load. And the average the difference is This is the rectangular shape. This is, I forgot to pick the picture. This is the picture. Let me put here. So P is the force, okay, the pulling force. LS is the length here for the average one. And the W is the width, okay. That's the area, okay, this is the area. Okay, now to understand the double shear, I forgot to pick the picture. Let me illustrate. So one is just the original, like this, okay. So you have bolts and nuts. Okay. And the other one is we have this. Okay. So in here you have two sections in between. So this is going to be like that. And here is just these two plane put together and put bolt here. So we can imagine that it will be. You will see that this one is just one-way shearing. This way, this has these two double shears. Okay. I hope my drawing clear. So this is. So imagine if we pull this, goes there, pulling over there, and pulling over there. Okay. Now if we draw simply in a free body diagram, so let's say this is A, this is B. So for A and B, so if we draw the A, maybe this is just as simple as that. This is B, and if we cut, okay, imagine cut the middle, maybe cut here. So we will have like that, and this will be P, and this will be the shear force, okay. So only one shear force that equal the P, okay, if we take that approach. But for B, the picture B, if we cut these pieces, okay, only look at the middle part. Okay, remember that we have something here, right? This is the connections, the pin connections. So when we pull down, if we take the free body diagram, we are going to have two forces in between this pin, okay, which is the, let's say, V2 and V3. And this will determine how the formula will be. So the first one, we developed that V1 is equal P, but for the second one, V2 plus V3 equal P. And we can say that the V2 equal V3 equal P over 2. So the average shear stress, so this is single shear, okay, this is single shear. This is double shear. So the difference is, for the double shear, you need to divide by 2. Okay? Divide by 2 for the shear force, for the shear force and the shear stress as well. Okay, I think better to have an example, but I think I will put the example on next week class. So next week I will start from reviewing a little bit shear, having example, and then shear strain, about shear strain. So imagine if you have some materials, but you're shearing the materials. Maybe let me explain a little bit here. If we shear this, okay, we shear this going up, going down. Okay. Perhaps this is going to be the material. Okay. Right. Imagine that it's like a jelly. You shear the jelly. You see some part of it going like this. Okay, this is after the shear. So what's the changing? How do we identify the strain for the shear? Is there any change in length? I think not much, right?
Angle?
Yes, angle. Before it's 90, but then it's decreased. That's the shear strain. Okay. We will discover more next week. Okay. Okay, I think I will finish up until here. I will put some exercise, although we haven't yet had an example. Later I will put maybe 2 or 3 exercise about the shear stress, shear strain, maybe just shear stress, and the previous one, the normal stress. Okay. I would like to prepare for quiz, but not next week. Maybe next 2 weeks. Maybe next 2 weeks. Okay. Next 2 weeks. Because I want to finish up until this shear. So that will be, or maybe the quiz just an early overview on statics and the normal stress. I think that's also okay enough. So please review your statics because this course is actually statics plus mechanical properties. Okay, I think that's